Hello students, welcome back to yet another session in unit number 5. So we are commencing the topic number 3 today, where we are going to discuss about internal heat load. So it is very simple topic. We can complete this in a very few minutes. So these are all the content in our unit number 5. Now we are discussing this topic, internal heat load. It is a very simple topic, and next session we are going to split the next topic, apparatus selection, fresh air load, and we are going to see in another subsession, that is human comfort and IAQ principles. So this is a very important topic also. So I am splitting this fourth part of this unit into two sub sessions. We are going to discuss that in detail, and then we shall discuss effective temperature and charge. Then we will move on to calculation of summer and winter air conditioning load, and then classification and layouts of plants. So these are the topics, and then we have air distribution systems and filters, air conditioning systems and controls, temperature, pressure, humidity, and the sensors and actuators and safety controls. So this we are going to discuss in our subsequent sessions. So components of internal load. So here the heat gain from occupants. So this is one of the component, and human bodies generate heat via metabolism. So heat gain depends on number of occupants. So number of persons who are sitting in that space. Type of activity, it may be seated, walking, exercising, and then we have clothing. So even clothes that the occupants wear, so that also here is one of the load only. And age and gender also one of the loads. So adjustments here, the male is the ideal load. So with the male, we can adjust the female and kids or children into the adult, that is the male adult percentage. So here a female is always considered to be 85% of adult male. So this is one small assumption or adjustment. So child is 75% of an adult male. So this is small adjustment we are making here. So with that, the typical values here, the activity level, it may be seated, office work, standing, and heavy work. So here the sensible heat is 53, 57, 73, 136 watts, and latent heat here is 44, 60, 51, and 288 respectively, and total will be 97, 117, and 124, 425 so watts. So this is the typical values from the observations, from research we can get these values. So heat gain from lighting. So definitely there will be lighting in every room or space, and lights convert electrical power into heat. So lights normally generates a heat, and a portion becomes sensible heat depending on the type of lamp. So normally we are getting from lights is sensible form of heat, and type of lamp also matters here. And to calculate the heat gain from lighting, so that is equal to wattage into use factor into allowance factor. And the use factor is actually the actual use versus installed wattage. So actual use versus installed wattage. So normally 1 for normal use and lesser than zero point 0.5 for intermittent. So allowance factor is nothing but for fluorescent tubes, typically 1.25 for ballast losses. So components here, the heat gain, the next one, third one, the heat gain from appliances and equipment. And appliances emit heat based on type, electrical, gas or steam, and usage pattern, whether hoods or ventilation systems are present. So example values are like this. So appliance, this is a coffee urn, fryer, toaster, sterilizer. So for this, the sensible heat gain is like this. It is 996 for coffee urn, and 1026 for fryer, 1495 for toaster, and here the wattage per hour is 360 per hour, and sterilizer it is 190, and latent is little variant here, and you can see the latent is 674, 1465, 1465, 380, 352. So gas-fired equipment emits a higher heat loads. So gas-fired equipments normally emits more heat, and latent load arises from moisture emission. So that is steam cookers. So even steam cookers in kitchen, that also exhibits heat. So next is heat gain from power equipment. So motors, fans. So power equipment normally present in every household, where motors, fans, pumps consume electricity and releases heat. So normally fans also in the space, air conditioned space, emits some sort of heat. So if located inside a conditioned space, heat adds to load. So suppose if it is within this space, air conditioned space, so it also adds heat to the load. So formula to calculate the heat gain from power equipment equal to Q equal to power rating kilowatt divided by motor efficiency or fan efficiency, whatever may be the appliance, into load factor. So load factor is the fraction of full load operation. So types of internal heat load. Now you can see the occupants, lights, lighting, computers. Even a computer is a gadget. Even that also produces heat, and cooking, food preparation, motors, fans, water heaters. So here all these exhibit sensible heat, and a few of these exhibit latent heat. That is occupants, cooking, food preparation, and water heaters, and whereas motors, fans, lighting, computers doesn't produce any latent heat. And now it is based on activity, and the lighting is 100% sensible, and the computers mostly sensible, and cooking, food preparation generates steam, so that's why you have latent heat, and adds mechanical and electrical load. And water heaters may generate vapors, so that's why we have the latent heat here in case of water heaters. So here one example, let us see. So 50 occupants in a restaurant, and 5 kilowatt of lighting. So it is one in use, and allowance is 1.25, two coffee ons, so 22 liters in total, 996 watt plus 674 watt each, and one fryer, that is 1 meter square, so that is equal to 1026 watt plus 1465 watt. So let us see its step by step calculation. So occupants is sensible, that is it also there will be latent also. 50 into 65, that is 3.25 kilowatts. So latent is 50 into 155, that is equal to 7.75 kilowatt. So lighting Q equal to 5000 into 1 into 1.25, so that is equal to 6250 watts. So that becomes 6.25 kilowatts. And appliances coffee urns, so 2 into 996 plus 674, so each one, so that's why it is 2 into 996 plus 674 equal to 3.34 kilowatts. And fryer is 1026 plus 1465, that is equal to 2.491 kilowatt. So this is the step by step calculation we will see in next slide. So effective room sensible heat factor, so that is ERSHF. So this is ERSHF in a short, and in exam if you get what is ERSHF, it is effective room sensible heat factor. So here ERSHF equal to total sensible heat divided by total heat, that is sensible and also latent. This is used in psychrometric analysis to plot sensible and latent lines, locate apparatus dew points, size cooling coil requirements. So design considerations, use diversity factors, not all appliances used continuously, account for intermittent loads, so that is food warmers, dryers. So factor in ventilation and infiltration, air interaction. So this is the summary chart, and occupants, it is activity dependent, light is fully sensible, appliances is depends on type, and equipment electric or mechanical. So here this is the summary of this chart. And now there ends this topic, and the reference books as usual you can refer any of these books. So R.S. Kurmi is a better book. You can refer R.S. Kurmi also, and this material will be sufficient for this topic. So then we have e-resources as well, and there ends this topic, students. We will meet again in next topic, and we will see there. So now we stop here. Thank you, students.